Dear colleagues, our report is devoted to the phenomenon of underground urban heat island below Moscow city and the long-term changes of it. My name is Mikhail. My co-author is Irina, and we work together about this topic during a long time already. About the soil temperature measurements. Soil temperature is measured mostly by classic traditional liquid thermometers. There were several attempts were made to replace liquid thermometers by new automatic sensors, but nevertheless, they are still used in Russian Federation in many weather stations. It is the most traditional instrumentation. They need manual readings, but they represent the most reliable type of measurements with very high accuracy, not worse than plus minus 0.2 Celsius degrees. And these mercury thermometers are surrounded by special copper filings for longer inertia, and they are installed into special ebonite tubes which have very low thermal conductivity that allows to measure this parameter. The measurements of the soil temperature was started in Russian Empire at the end of the 19th century. So it has a long history of these measurements. It's me several years ago where I was younger. The soil temperature is measured at our Moscow University, at Meteorological Observatory of Moscow University, simultaneously on two sites, below natural cover and below special naked area. Measurements are carried out continuously during the last almost 70 years, since 1955. Soil temperature is measured on 11 depths, up to 3.2 meters below the ground. This is the deepest level of measurements. And you can see special naked area, which is naked always. Both snow cover and grass are removed from it. And you can see some words about climatology of the soil temperature. You can see the annual course of the soil temperature at Moscow by the data of Moscow University at different depths. And evidently, an amplitude of the annual course reduced with depth. So the deeper is the level of measurements, the less is this amplitude, according to the first Fourier law. Besides, the annual course delays with the depth accordingly to the second Fourier law. It is not a surprise that because below naked area, the amplitude of the annual course is much larger than below natural cover. It is a result of influence of snow cover, grass, and sod cover, because snow, sod, and grass smooth changes of temperature. You can see profiles, monthly average soil temperature, profiles of soil temperature for different months on both locations, on average of 45 years. And you can see an average profile of mean annual values of the soil temperature, red circles, and this profile demonstrates near the same values along whole the range of the measurements, up to the deepest level, 320 centimeters below the ground. Then, the dynamics of the soil temperature. On both locations, we can see a warming. Soil becomes warmer, but below naked area, warming is faster than below natural cover. It is interesting, it is important to study the centennial changes, long-term changes of these parameters by the date of the long history of these measurements, which were started at the end of the 19th century. We used the data of the oldest weather station of Moscow city, Mikhail Observatory, which operates since the end of the 19th century. And you can see total row, combined row of data. Values of both weather stations are close to each other in time of intersection. So it allows us to consider that combined row is almost homogeneous. So we can study long-term changes. Linear trend demonstrates steady warming of the soil temperature in Moscow city, and linear regression coefficient is 0.01. It means that average rate of warming is 1 Celsius degree during century, 0.01 per year. Then parabolic trend, red line, almost coincides as linear trend. Cubic trend, green line, is close to both other trends, and only the most complicated polynomial trend of the 6th degree demonstrate an additional feature, acceleration of the warming during recent decades. So let us discuss the phenomenon of underground urban heat island. Evidently, urban heat island is three-dimensional phenomenon. It extends both upward and downward into the soil. What are the reasons of this phenomenon? First of all, it is total downward heat flux from warmer urban air into the soil, because urban air is warmer than rural air. Besides, local heat fluxes influence on the soil temperature as well. Heat fluxes from separate anthropogenical objects, such as separate buildings. Besides, one more factor is changes in surface cover of an urban area. Besides, one more, less heat and heat loss because of lower evaporation from drier urban soil as a result of man-made runoff of precipitation. One more factor, influence of the underground urban heat sources, direct heat fluxes from subway, from underground heating pipes, etc. And runoff of warm industrial and domestic waters, urban warm waters, the runoff into the soil leads to an additional warming of the soil. Depression funnels below big cities as a result of drop of cool underground waters below the city and underground fires. So this phenomenon of underground urban heat island is a result of a lot of factors, a lot of different factors. Detailed mapping of this phenomenon was made according to the old data, because in the middle of last century, the density of weather stations which perform measurements of the soil temperature in Moscow region was the highest. Unfortunately, later, the number reduced. So detailed mapping is possible only with the use of this old data of 1960. You can see detailed mapping at each separate level, surface, 20 centimeters, 40 centimeters, 6 centimeters. Each time we can see 1 or 2 or even 3 isotherms with a step half a degree, which are closed or semi-closed. And they confirmed an existence of the positive thermal anomaly below the city. So 120 centimeters, 3 semi-closed isotherms, 160, 240, and then finally the deepest level, 3.2 meters below the ground. We can compare the data of 1960 and the data half a century later. You can see that indeed, unfortunately, a number of stations reduced. In the middle of 20th century, 13 stations operated in Moscow region, which performed measurements of the soil temperature, 5 urban stations and 8 rural stations. Now only 5 stations, 2 urban and 3 rural stations remained, which performed these measurements. But underground urban heat island are clearly seen in both cases. Evidently, it extends or deep levels below 3.2 meters. But unfortunately, weather stations do not measure soil temperature below this level. But we found in the literature old results of measurements which was made by Prosenkov in 1974. He compared measurements of 35 deep chinks, and he presented special field of the temperature of underground water. A positive thermal anomaly is clearly seen, even at this depth, 30 meters below the ground, neutral layer. But it is slightly another object. It is not soil, it is underground water temperature. So, an intensity of the underground urban heat island is calculated as a difference between soil temperature inside city and outside the city. You can see profiles of the soil temperature, and on the left part of figure, profiles of this intensity according to two versions of this parameter, intensity 1, intensity 2. And as you can see, an intensity of the underground urban heat island in Moscow varies from 0.3 to 1 degree, to 1 Celsius degree. And the annual course of this parameter demonstrates clear maximum in cold season from October to April and the minimum in summer when intensity is close to zero or is even slightly negative. This maximum is explained by urban heating in winter, in heating pipes, which creates an additional heat flux into the soil. So, the next question is, what is long-term dynamics? What is long-term tendency of the underground urban heat island in Moscow? The first step was the use of the data of only two stations, our Moscow University urban station and rural station of Moskovne, which is located 25 kilometers to the west from the city. It is preliminary analysis. What is the result? Soil becomes warmer at both locations, both in the city and outside the city. But at rural station, warmer is faster. You can see the value of linear trend at Podmoskovna is 0.03, whereas in the city it is only 0.02. So warming outside the city is a bit faster than inside the city. You can see distribution functions of the values at both places, both locations. These functions confirms an existence of positive anomaly because model value of the urban stations is higher than model value of rural stations. Both functions are close to normal log according to his square test, so we can use classic student criterion, parametric student criterion, to check statistical significance of the change, statistical significance of long-term change. We calculated two partial samples, first 15 values and the last 15 values, compared them, and the received result difference is statistically significant with very high confidence probability. So a warming of the soil is real, statistically reliable effect. As regards intensity, surprisingly, trend is negative, slightly negative. It was preliminary analysis. The next step was more detailed analysis with the use of data of all 5 stations, both urban stations and 3 rural stations. You can see tendencies of the soil temperature at all 5 locations. A warming is detected at all sites, and you can see that at rural sites, at rural stations, warming is faster than at urban stations. And intensity on 2 depths, 160 centimeters, 320 centimeters. Linear trends, parabolic trends, cubic trends. So we can use the same student criterion, and we received the result that statistical significant weakening of the underground urban heat island took place. It is surprising, unexpected result. In fact, the underground urban heat island became weaker than it was before. Why? Possible explanation. Firstly, weakening of the urban influence on the soil, probability of this factor is extremely low. Second, strengthening of the anthropogenic heat flux to the soil in small towns and villages in Moscow region, probably because every weather station are located close to small town or small village. And thirdly, maybe some changes of the soil moisture took place because drier soil is warmer. Probably either second or the third reasons took place or together. It should be noted that classic urban heat island in the air. It will be topic of my another oral report after tomorrow in Moscow. does not grow. It was stabilized during recent decades. It does not grow. So it is indirect confirmation of the weakening, surprisingly weakening of the underground urban heat island in Moscow city. Conclusions: the soil temperature in the layer up to 3.2 meters in Moscow significantly increased during last 125 years. Secondly, the underground urban heat island is real phenomenon, and its intensity is varies from 0.3 to 1 Celsius degree. And three, during last 45 years, the underground urban heat island in Moscow demonstrates statistically significant weakening, the reason for which are not completely clear. Thank you for your attention.
Questions? Questions?
This is super impressive data set. Amazing. I was wondering, because in the soil temperature measurements you showed at the beginning, where you have one under bare soil or clear soil and one under grass, you said you also cleared the snow of the clear soil. Do you see any effects of insulation of basically summer heat under snow-covered soil temperatures, in that like snow-covered areas have warmer groundwater temperatures in winter than not snow-covered stuff? Is there anything like this you're seeing? I've heard about this may be a factor, the insulating of the warm soil due to snow.
Insulation,
Yeah,
solar insulation.
yeah.
Really, it is real effect. We, together with Mikhail, carried out special experiments in our observatory. We made measurements in two close locations. One below shadow, another below direct insulation, and we found a significant difference. But I think that this result is real because we choose a temporal period when measurements were made at the same places without replace of stations. Why we did analyze the period from 1967? Because before, at one of stations, measurements were replaced. So we took into account only the time when sites of measurements were the same. Regarding type of soil, uh, special field is homogeneous. Almost all stations, soil of almost all stations are clay. Only one station is semi-sandy. Regarding snow cover, we have flat relief, so snow cover depth is almost the same over Moscow region. So we hope that this result is real.
Thank you very much.
Thank you very much. Very interesting.
Thank you.
Talk. We have to move to the next speaker. So our next presentation is an intercity comparison of subsurface climate, anthropogenic and hydrological factors, presented by Dr. Nicholas Maxis from University of Surrey / University of Cambridge.
Thanks. Good afternoon, everyone. My name is Nick. I'm a future fellow at the University of Surrey. And first of all, thanks for sticking with me for this last presentation of the day. Today I'll be presenting some work that I did as part of my previous post at the University of Cambridge, along with a number of collaborators from the University of Berkeley, UNSW here, KIT, and the Alan Turing Institute in the UK. So I'll be talking, like others in this session, I'll be talking about the subsurface urban heat island effect, which essentially is how our underground, our subsurface is heating up under urban environments. And this is significant because the thermal state of the subsurface can be important. Susanna mentioned how it can affect groundwater and drinking quality. In addition, it can affect a number of things like thermal comfort of underground spaces, groundwater and ecosystems. It can also affect underground good productions, which is kind of increasing recently with underground farms. This does include quality of wine in underground cellars. And we've heard about the anthropogenic impact. And just to exemplify that, I'm showing here, this is an advertising post for the London Underground about 100 years ago, where it was advertised as a place to go when it was a hot day to cool down. 3 years ago, these are the temperatures that were reported in the summer in the London Underground. Definitely not somewhere to go and cool down, and anyone who has been in the London Underground would know it's suffocatingly hot. Again, as mentioned, the fact that the ground is heating up is providing an opportunity to utilize that heat to sustainably provide heating and cooling energy, for example, through shallow geothermal systems, and identifying where in a large domain in a city we can invest can be valuable advice to organizations, to city councils. This is a relevant study in the city of Vienna, for example, by Thyssen, and I think Susanne, you're also involved. So our work essentially introduces kind of a methodology, a modeling methodology, to quantify the thermal state of the subsurface at a larger scale. And essentially, we want to go to from a, I don't have a pointer, but to, here we go. So from kind of a model domain or a chosen region to a set of underground thermal maps. To do that, we're introducing a series of steps, and I'm briefly going to go through this. And basically, to do that, I'm going to adopt an area in central London as an example. This is Westminster and Kensington and Chelsea, for anyone who's familiar. But the first step in this methodology is dividing the domain. So we take our chosen area, our chosen domain, and we divide it down into a grid. In this example, we're using 200 by 200 meter grid. It can also go, it can depend on the scope of the work, but the kind of smaller you go, the higher resolution you're going to have, but the more computationally costly it's going to be. The second step is the most time consuming because it's about data gathering. So we call it feature identification, but it's essentially getting the data and all the features that are relevant to the thermal state of the subsurface, both from the natural environment, the geology, for example, hydrology, as well as, again, the anthropogenic and the built infrastructure, the metro tunnels in the case of London, the effect from the buildings, the footprints, the basements, the heated basements, the sewers, which for London we had the kind of highest barrier in finding any information because the sewer network is considered high risk and is sensitive information, so we did have to make some assumptions. So having all of our features and essentially having a data set that we believe characterizes the thermal state of the subsurface or affects it, we go into step number 3, which is low fidelity modeling. So in this stage, we kind of run, in our case, finite element modeling, but we run these very quick models, a couple of minutes, throughout the domain with the main aim to identify a metric that we believe is representative of the thermal state. With the kind of nature of the low fidelity of the modeling, in this case, we're using the volumetric temperature of our blocks. And I've highlighted here the upstream temperature. So this is the temperature of the groundwater flowing into these blocks, this grid that we've split our domain into, because this is the only parameter we don't really know. And because of the nature of the methodology, this is a parameter we will have to parameterize. So we use a number of different values where it is applicable. So going into step number 4, essentially we have our features, which we believe are causing the thermal state, and then we have a metric that quantifies it. So we use statistical clustering to help us get some insights into the subsurface. In this case, I don't know how visible that is, but we're using regression trees decision trees, which is a statistical approach where you take the data set that you have and you split it based on the feature that most impactfully kind of affects the thermal state. So we keep splitting that down, getting into these groups of blocks that have similar features and result in a similar state of the subsurface, and we call those archetypes. And those archetypes are then a much smaller number, 10, 20, 30, that represent the entire domain, which can be thousands of blocks. And having that, we then go into modeling those much smaller number of models into high fidelity. And when we do that, we kind of combine sequentially step 5 and 6 because we need to take account of the ground continuity, specifically groundwater. So we create a directed graph that shows us how groundwater flows within our domain, and starting from upstream, starting from where we have information, we don't need additional information. We compute those blocks, those archetypes, and then sequentially kind of go recursively to compute the rest of the domain. It's very brief, but essentially that is the methodology, and we have applied that into 3 different locations in the UK and in the US. So this is kind of the example I went through in central London. We also have Berkeley and Cambridge. And applying that approach to these locations, we can get, for example, temperature maps. This is at 15 meters below the surface, but obviously we can get information at different depths based on the inputs that we used and the modeling that we did. So looking at the 3 locations here, we can see kind of very different behaviors of the subsurface, very kind of different temperatures and different patterns. For London, we have a very developed underground. We have tunnels. We have a lot more basements, a lot more. We have a large park in the middle, and we see kind of that distinct behavior as we go with depth. For Berkeley, essentially, we see very little influence, mainly because the ground in Berkeley has a very high natural temperature by itself. We were talking about 10-degree difference. In Berkeley is about 18 to 19 degrees. So then it has much less influence anthropogenically, and then you get into a homogeneous kind of temperature after a certain depth. And then in Cambridge, what we see here is a uniform influence because of the kind of dense population in the city center, the dense infrastructure, the nature of having heated basements throughout. So most basements in Cambridge are going to be heated. We see this essentially uniform influence that reduces with depth, but is still present. We can then take that information together with the data that we gathered in stage 2, and we can turn that into insights and further insights. This shows specifically the geothermal potential as kind of displayed through these domains. And we can see how essentially what the depth represents here is choosing a depth up to which to utilize in the subsurface. And that can depend into different types of ground heat exchangers you can have for your system, but it can depend on the construction, the project, and so on. But essentially what's kind of interesting here, if I kind of focus on Cambridge for this, we can see that if you are going to use the very shallow subsurface, in this case up to 15 meters, it can be quite significant where you're going to have your project, where you're going to construct, and which part of the domain you're going to utilize. You can have up to kind of double the amount of energy. While if you go deeper into the subsurface, it all becomes quite the same. So then it becomes less relevant where you're going to drill, where you're going to have your project, and that kind of can be an additional or one less constraint for the developers. So in conclusions, we've kind of talked about a large-scale thermal quantification methodology, applied that into 3 different urban environments, and kind of exemplify how we can create an kind of a series of thermal maps, understand how the subsurface heats up, and then how we can use that for shallow geothermal energy. The relevant paper is here, and thank you very much for your attention.
Questions?
Thank you very much for the presentation. I'm wondering, with your prediction of the geothermal potential, is there any way that can be verified how true these maps are? Have they been used somewhere, or?
We haven't been used quite yet. In terms of verifying the potential itself, it kind of depends how you do the geothermal quantification, which I kind of glanced over because it wasn't the focus here. But the maps that we created here are basically using kind of established analytical methods like line source heat transfer theory to identify comparatively based on the temperatures that we predict, based on the natural environment that exists, the geology and so on. You kind of get the result and compare how much energy you can extract. But this is all very kind of comparatively given same circumstances. But when you go into a real project, you're going to have to think about what do you use the heat for, the patterns of the kind of the demand of heat, and you can kind of optimize it much more.
Yeah. I was just wondering if those are something you could sell to the industry, like if they would prove that this actually works.
We have been. I mean, we kind of part of the start of this work was around Cambridge, working with the different colleges and the council to kind of advise as to where it's more beneficial. And this is a good kind of first layer. But then when you go to the real project, you do also have additional constraints. Some people don't want to dig into their garden because it's part of a nice, fancy college, or some people. Then you have additional constraints with cost and so on. But yeah, thank you very much.
Any more questions?
Actually, very interesting talk. I was wondering because if we implement a lot of ground source heat pump, for example, and then that also changes the underground thermal properties, and you have very interesting, I think, modeling framework. Do you think in the future maybe there's a way to incorporate that with modeling framework so that we can have a better idea?
Yes.
Respond on the feedback.
Yeah, 100%. That's very very good point, because this kind of approach, which is too blurry to say, I'm sorry, essentially is used to quantify the state of the subsurface as it is based on the information that you have. And adding additional ground source heat pump systems is essentially adding another feature back on this stage too, which will then affect the results. But the nice thing about this methodology is that it's expandable. So essentially, when you come to these archetypes, you can then expand your analysis, add additional models which have those additional ground heat exchangers implemented, and then this tree just expands to be able to then account for that and update your results. Yeah.
Well, thank you very much.
Thanks.
Thank you very much to So if there's more questions, you can definitely take it outside the room, but that's the end of the session. Thank you very much.